Welcome to the first lecture on quantum mechanics. So in this lecture we will only talk about the mathematics that we need to use to understand the quantum mechanics. So let's start with the set. Now I will just give you a brief on what a set is. So a set which we have learned so far is from the naive set theory. It says that the set is a collection of objects. So a typical example would be this. So it's a set with a finite number of elements, and another example would be a set of natural numbers or real numbers. Now the problem with this formulation is that it defines what a set is, and so it says that a set is a collection of objects, but as mathematicians advances this set theory, they discovered some paradoxes like the Russell paradox. So for Russell, which was a mathematician, he discovered some set which cannot be defined, and so he wrote a set like a set that contains all sets. So this type of set cannot be defined, so this naive set theory didn't work. So instead of this set theory, an axiomatic set theory was introduced. So this is called the ZFC. The full form is the Zermelo-Fraenkel set theory. So these are two names of the mathematicians. Now this set theory provides you 9 axioms, and the theory itself will not tell you what a set is, but this notion of set is a primitive notion, so it cannot define what a set is. It's just like in Euclidean geometry, you cannot define what a line is, you cannot define what a point is, but you have an intuitive feeling about it. So just like that, axiomatic set theory, you do not define what a set is, but you do know how to manipulate sets, how to do operations with them. So these 9 axioms tells you how to manipulate sets and do operations like union, intersection, and complement. So we will not deal with such subtle notions, but that was just a recap. Now we will define what a vector space is. So vector space. What's a vector space? So you have a set V and 2 binary operations, a notion of addition and a notion of scalar multiplication. Now under this structure we have a notion of field. The field F is a mathematical notion, not a vector field or a scalar field. It's just like real numbers or complex numbers. So they form a field. Just it's a bit same structure as vector space, but have more properties. So we define an addition of 2 vectors. So you take, that's a mapping from V cross V to V. So you take 2 vectors V and W and map them to their sum. So you take two vectors and map them to their sum, and now this sum must be contained in V. So there's a notion of addition of two vectors. Now the scalar multiplication, it takes an element from the field. So we will only talk about the complex vector space in quantum mechanics. So you take the complex field and the vector space and map them to vector space. So you take a complex number, say alpha, and you take a vector V and map them to alpha times V. So you can multiply a vector by a complex number. So there's a notion of scalar multiplication. That's why we see a scalar, because we are multiplying by a complex number. And here we are adding two vectors and obtaining another vector. So there's a notion of addition. Now, with these two binary mappings, there's a notion, there are certain number of axioms that needs to be satisfied to be a vector space. So we'll write those axioms. So I can write them as C A N I A D D U. So the C here means the commutativity in addition. So if you take two vectors, V plus W, it must be same as W plus V. So the addition commutes, and this must be true for all the vectors in the vector space. So commutativity in addition holds, and the associativity tells that V plus W plus Z is equals to V plus W plus Z. So this is the notion of addition. It doesn't matter where you put the brackets. So the brackets can be, so these brackets can be changed. So the position can be changed, it doesn't matter. So I can simply write them as this. So I don't need to put the brackets when I just add vectors. So this must hold for all the vectors in the vector space. Now the neutral element says that there exists a zero vector in the vector space. So it says that there exists a zero vector in the vector space such that if I add any vector to it, it will simply give me that vector. So there's a notion of null vector in the vector space. These are all existence axioms, and these are need to be satisfied for any set to be a vector space. So this must also holds for all the vectors in the vector space. All right, so this is the inverse. Now it says that for all the vectors in the vector space, there exists an inverse of the vector minus V with respect to the addition, such that V plus minus V gives 0. So there's a notion of inverse of every vector, or with respect to the addition, so it must hold for all V. So every vector has an inverse, such that if you add the vector to its inverse, you get a null vector. So this is associativity in the scalar multiplication. So if you take two numbers, two scalar numbers, lambda and mu, and you multiply them, so that's a multiplication between two complex numbers. So that's why I put a dot here, and I put a double dot and then a vector. So that is a scalar multiplication here. So let me enlarge this a bit. So this is a scalar multiplication. So that's a complex number, because if you multiply two complex numbers, you get a complex number. So a complex number times a vector must be same as lambda times, so that will be a scalar multiplication again, and that will be mu times V. So it says that you can shift the bracket here, but now you must clearly see the dots here. These are scalar multiplication, and this is a multiplication between two complex numbers. So that must hold true. Now this is the distributive property. So it says that lambda plus mu times, so that's a scalar multiplication, and times a vector is equal to, so it's the addition, then the scalar multiplication distributes in the addition of two complex numbers. So it says that lambda scalar multiplication v is plus mu scalar multiplication v, v. So this must hold for all complex numbers. So lambda, mu are in complex numbers and v is in capital V. So it is also implied here. So this property must hold. Now, instead of two complex number, I take the addition in two vectors. So it says that lambda times, now this is scalar multiplication, and this is v plus w is equals to lambda scalar multiplication v plus lambda scalar multiplication w. Now this must hold for all lambda in complex numbers and all vw in vector space. Now here, this addition is addition between two vectors, and this was the addition between two complex numbers. So these are two different properties. And the last one is that the multiplicative identity exists. So there's a number 1 times a vector must return the vector v. So this is the multiplicative identity for scalar multiplication, and it must hold for all vectors in the vector space. So these are the 8 axioms that we need. And whenever we talk about vector space, when we will do examples, we need to verify these 8 properties. Now let's see some examples of some vector spaces. So the first example would be Rn. So we all know this. So let's take two vectors v, w in Rn. Now, if you know the concept of bases that are linearly independent vectors, then you know that these v and w can be written in terms of standard basis as v1, v2 up to vn, and similarly w can be used as w1, w2 and to wn. So now we can define the addition of two vectors as v plus w is equals to v1 plus w1. The corresponding coordinates can be added together. So this is v2 plus w2 and up to vn plus wn. So that's the notion of addition that I define here. So it's a coordinate-wise addition. And similarly, I can define the scalar multiplication. Let's take a lambda to be a real number. So I define lambda times a vector as lambda v1, lambda v2, and lambda vn. Now, I have defined these two mappings. I have defined a notion of addition, and I have defined a notion of scalar multiplication by a real number. Here, lambda is a real number. Now, it is up to you to prove that the axioms that I stated earlier are satisfied in these two operations. So then we say that Rn is a real vector space because the underlying field of this vector space is real, is the real field. So Rn is a real vector space. So similarly, I can have an example too of the complex numbers. So here C is a set of all the complex numbers. So C is the set of all complex numbers. So any element, any z in C can be written as x plus iy, where x, y are real numbers. So now I can define an addition between two complex numbers. That's very easy. So z1 plus z2 is x1 plus x2. You just add the real parts and you add the imaginary parts. And similarly, I can define a scalar multiplication. So alpha, let alpha to be a real number. I can define alpha times z1 is equals to alpha x1 plus I alpha y1. So I have defined these two mappings as a notion of addition and a notion of scalar multiplication. So now you can easily check that all those 8 axioms are satisfied, and the set of all complex numbers under the real field is a vector space, is a real vector space. Now let's take a different example. So this is all the continuous function on the interval AB, where A, B are real numbers. Now, so what are the elements of this set? These are continuous functions. So f belongs to C, AB implies that f is a continuous function on AB. So now I will give you an exercise for this, that you have to construct its mapping and a notion of addition and notion of scalar multiplication by real numbers, and you have to prove that CAB, the collection of all the continuous function on an interval AB, is a vector space. Now when we will talk about the basis of a vector space, then we will show that the CAB is an infinite dimensional vector space, not just like Rn or any complex vector space. The number of basis vectors that are linearly independent and spans the vector space are infinite. So now let's talk about some more structure on the vector space. Now so far we have this structure, V, a set with a notion of addition and a scalar multiplication. So that's a vector space. Now we will add a notion of length of a vector. So we will define what does it mean for a vector to have a length. So we will define a mapping. So this is called a norm. So right here, so that's a norm. So it takes a vector from the vector space and maps them to a real number. So it takes a vector and map them to a real number. So it is not just a simple mapping, there are axioms. So first axiom is that norm of a vector V must always be a positive number. And this equality holds only if V is a zero vector. Okay? And the second property is that if I take lambda times V, this must be same as magnitude norm of lambda times a norm of V for all lambda in real numbers and V in the vector space. And the third property is it's the triangle inequality. So it takes the V plus W is always greater than or equal to magnitude of V. No, it's the other way around, I think. Yeah, magnitude of V plus magnitude of W for all V, W and the vector space. So these are the property of a norm that must be satisfied to associate every vector a notion of length. So you can write this as a length vector. Now let's first talk about a notion of inner product. Then we will talk about how do we define a norm on the vector space using an inner product, because that's what we need for the quantum mechanics. Okay. So let's first talk about the inner product. So just like a norm is a mapping, the inner product is also a mapping. So let's define it. So it takes two vectors. So these are open slots. So it takes two vectors and map them to, for a complex vector space, we can define this to be a complex number. So just like a norm, it has to satisfy three conditions. It says that a norm of VW, it's the inner product of VW, two vectors, must be equal to WV. You swap them and take the complex conjugate. Because that's a complex number, you can take the complex conjugate, and this must hold for every vector in the vector space. And the second property is the sesquilinear property. So it says that V, alpha W plus beta Z is equals to, so it must be linear, so alpha comes out, but there's a conjugate here. So that's a conjugate, so this is VW plus beta conjugate, and this is VZ. And this must hold for every vector in the vector space and for every alpha beta in C. So this property is called the sesquilinear property. Now the third property is that it is positive definite. So third property I will write here. So it's the positive definite property. So it says that if I take the V inner product with V, it must always be greater than or equal to 0. So it says that now this inequality holds if the vector is itself a 0. Now let's introduce the notion of norm. Now let's do some first examples of some inner product. Now for Rn, let's take an example Rn. We will introduce a notion of inner product. So I take two vectors, V, which is equals to V1, V2, and up to Vn. And I take another vector, W1, W2, Wn. So I define their inner product as VW is equals to, I multiply their corresponding coordinates. So that's right, I from Vi, Wi, and I goes from 1 to n. So we see that in this case it's a real number because the vector space here is a real vector space. So it can be a complex number if the underlying field is complex. So you multiply two numbers here and you get an output that's a real number. Now you can check those three axioms are satisfied with this definition. So that's a definition, and that's an inner product. Now using this inner product we can introduce a notion of norm, a notion of length. So let's use it here. So you define a norm of a vector as, you take the square root of V and inner product of V with V. Now you know that it is positive definite. That means you can take the square root, because you cannot take the square root of a negative number because the norm must be positive. So we can again use those axioms to verify that this is indeed a norm. So we have covered the notion of norm, inner product, how to introduce norm using an inner product, and we have the notion of vector space. Now let's define a sequence. So now we define a sequence on a vector space, a sequence. So a sequence is a map from natural numbers to a vector space. So to every natural number you associate a vector. So for example, f of n, you associate a vector vn. So that's a sequence. You can write this as v1, v2, v3, and since there are infinite number of natural numbers, this length and the sequence is infinite. Now we're going to define a particular type of sequence that's called the Cauchy sequence. So let's define it. Because these are the notions that we will use in quantum mechanics. So let's define a Cauchy sequence. So what is a Cauchy sequence? So a sequence which is a map. So I'll write here, a sequence is a map from natural numbers to vector space. A sequence is called Cauchy if and only if for every epsilon greater than 0 there exists a number n in natural numbers such that the norm of Vm minus Vn is less than epsilon for all Mn and for all Mn greater than or equals to n. So it says that given a sequence, that means a collection of vectors v1, v2, v3, v4, and for every epsilon that I receive from someone, so someone says an epsilon, then I must find a natural number. I must find a natural number according to which, after which the distance between the sequence tends to 0. So as the sequence proceeds, so it's like v1, v2, v3, v4, the consecutive terms, they are getting closer and closer to each other. So if I get a pictorial picture, let me say, so let's say this is v1, this is v2, this is v3, this is v4, this is v5, this is v6, this is v7, this is v8. So we see that the distance between the consecutive terms is getting smaller and smaller. So that's a typical property of a Cauchy sequence. The distance between the terms of the sequence is getting smaller and smaller. Now the Cauchy sequence does not tell us about the convergence. It does not tell us about whether the limit exists. It just tells that if the distance between the terms getting smaller and smaller, then it will be termed as a Cauchy sequence. Now, we have developed so far all the necessary material to formulate the quantum mechanics. Now, we will now talk about the Hilbert space. This will be the arena where all the fun happens. So a Hilbert space, let's denote it by H. First, it's a vector space, so it must have a notion of addition and a scalar multiplication. Now, once it is a vector space, we have to define a notion of length of a vector. So for a length, for the norm of the vector, we need the inner product. So let's add an inner product 2. Now, with a vector space structure, it has an inner product, then we have an inner product space. Now, using this inner product, we can introduce a norm, because for any vector in the Hilbert space, I can define a norm. So you see, I have used the inner product to define a norm. So that's a typical property of a Hilbert space, because Hilbert space are all those vector spaces where the norm is being introduced by the inner product. Now, it's just not the inner product space, we have further conditions. Now, the further condition is that every Cauchy sequence must converge. So the next condition is, first, it is a vector space, it has an inner product, and inner product must introduce a norm, and then every Cauchy sequence in this vector space must converge. So this whole condition can be written in a single word called completeness. So either you say that every Cauchy sequence in the vector space must converge, or you can say that the vector space is complete with respect to the norm introduced by the inner product. So that's a typical property of a Hilbert space. So once you have done that, you have got the Hilbert space. So I think so I have introduced the notion of Hilbert space. And you see that, and you will recognize that in classical mechanics we deal with the Hamiltonian equations, the Lagrangian equations, and the Newtonian dynamics, where the evolution of the system happened on a phase space. So that's P, I think that's Q, and that's P, and the system evolved according to the Hamiltonian equation from an initial point Q1, P1 to a Q2, P2. So, and the evolution is deterministic depending upon the Hamiltonian equation and the initial condition. But here, the underlying arena is the Hilbert space, and as it turns out, the Hilbert space underlying every quantum system is in fact infinite dimensional, and this is pretty much bizarre for any student, because so far he has learned about the phase space, which is a 6n dimensional configuration manifold, but Hilbert space, it is much more than that, and it is quite different from this. So in the next video I will talk about the postulates of quantum mechanics and how